It may be true that engineers don't read manuals, but this may be the only exception. It's a data sheet, and it contains everything you ever wanted to know about your logic device. In this episode, we're going to open this up and understand just why all this information is here and what it's useful for. You may be thinking, why are you showing me how to read a data sheet? After all, it's all spelled out clearly, right? The fact is, there's a lot of information hidden in a data sheet that if you know where to look for it, it can answer a lot of your common questions. Now, we could just read one from cover to cover, but that would be pretty tedious. So instead, let's look at the most common questions that we get about logic devices and show you where the answers can be found. Does this device have Schmitt trigger inputs? A Schmitt trigger, of course, is a type of input that helps reduce noise by making sure that the voltage swings well into the high or low states. It also has hysteresis to make sure that the voltage swings far enough one way before it swings back for a new transition. If you look right here on the front page, you will see that it says Schmitt trigger actions. Is this the answer? Well, no, it's not. You see, there's a difference between a true Schmitt trigger and a Schmitt trigger action device. Action really just means that the input threshold voltages have been adjusted to make them less sensitive. But if you look further down in the data sheet, you'll find that there is no information on hysteresis, which means that this particular device does not have true Schmitt trigger inputs, just action. Got it? By the way, while you're looking at that front page, always make a note of the revision history at the top of the page. Always make sure you're using the newest version. It will save you a lot of time in the long run. Now, some of the more mature parts don't get updated that often, but if you're working with one of the newer logic families, always check to make sure that you're getting the latest data for your part. What packages are available for this device? Most logic devices come in 2, 3, or even more package types. This information can be found on page 2 under Ordering Information. The actual physical dimensions for each of these packages are shown further down in the data sheet. Now, the other useful information here is the actual SOT number. This is the industry standard package definition. This makes it easier when you're laying out a board because most schematic capture programs already know the dimensions for these common parts. So you don't need to go out and create a package from scratch. The functional diagram tells you not only the function of the device, but it also matches the symbols that you would find on your schematic capture tool. You can also see how many copies of the gate are inside some multi-gate packages. How should I connect that large center pad? This is the most useful page to use in the lab when you start wiring up your prototype. This page shows you not only the pin numbers, but also the location of pin 1 for the different types of packages. Remember that the diagram is always shown from looking down at the top of the package. If you're actually soldering wires from the bottom of the package, remember it's a mirror image. Now notice on the right-hand diagram the footnote under the DHV QFN package. It regards that large soldering pad in the middle of the device. A lot of people wonder what to do with it. The pad was originally created as a heatsink for high-power devices like amplifiers that happen to share this same package. Now, logic doesn't dissipate much power, so it really doesn't need this heatsink. So the footnote tells you what to do with it, which is usually to leave it alone, let it float, which seems to go against common thought. But always read the footnote and follow it. Why are there 2 sets of specifications for each part? This is probably one of the most confusing parts of the entire data sheet and probably creates the most questions. The recommended operating conditions are the parameters that you should always use for your design. They give the minimum and maximum voltages and currents that the device should see. If you stay with these values, you will have a solid, stable, and reliable design. So why are those limiting values listed here then? Why are they shown to be so much higher? And can you design a circuit that uses those bigger numbers? Now, the limiting values really just give you an indication of the headroom or the tolerance of the device. Perhaps you find that when your circuit first powers on, the supply voltage of VCC goes to 5.8 volts for a brief period of time. Now that is above the recommended value, but still within the limiting values. So what's the impact of the device? The answer is probably none. But the fact of the matter is that there is no test data to prove that one way or the other. The limiting values are the widest extents of the testing for this device. The part doesn't catastrophically fail at these values, which means the magic smoke comes out of it. But it doesn't mean that you can run the part all the time at this level. Because of the higher voltages and currents, that the device will be overstressed and its lifetime will be impacted. However, there is just no way to know exactly how much because there's too many parameters. The moral of the story is, design to the recommended values. If you exceed the limiting values, you are asking for serious trouble. However, if you are in the no man's land between recommended and limiting, use your engineering experience to assess the impact to the overall reliability of your design. Is this part overvoltage tolerant? Overvoltage tolerant means, can you put more voltage on the input or output pin than the supply voltage of VCC? The answer is right here in the recommended value chart. If the value listed is VCC, like for Vout, then the answer is no. Because as VCC drops, then the Vout must also drop because it can never be higher than VCC. But notice the max value for the V input. It's listed as 5.5 volts, which means even if you power the device with only 2 volts, you can still let the input see 5.5 volts. It is indeed overvoltage tolerant. What's the difference between AHC and the AHCT version? You may have already noticed that this data sheet covers both the 74 AHC14 and the AHCT14 device. This is because they are essentially the same part, but the T device has been characterized for TTL supply levels. Since this is a smaller voltage range than the AHC device can handle, make sure to reference the right sections in your data sheet. How much output current can this part supply? The static characteristics are the voltage and currents that the device can operate at if you hold the inputs or outputs in one state. Now this is different than the dynamic values, which are listed below, which indicate how fast the device can change from one state to another. The static values tell you the drive capabilities of the device. As the current drawn from an output pin increases, it gets harder and harder for the device to reach the proper high and low signal levels. So depending on the supply voltage of the device, this chart gives you the voltage levels that you will see at the pins based on how much current you draw from it. Notice that the highest current listed is about 8 milliamps, which is generally the maximum drive current for the AHC family. Note that there are 5 different voltage current combinations listed for this device. But what if you want to know a value which is between there, which is not published? Again, you are working in undocumented space. But fortunately, you can get a fair estimate of the value by graphing the given values and interpolating between points. The relationship is pretty much linear between each set of points. But remember, always use your engineering experience here. How much power does this device use? Often it's important to know exactly how much power a device will use. This can be found from the values of ICC, which is the base amount of current that the device needs. However, the inputs also impact the total amount of power consumed, and this is reflected in the delta ICC, which tells you how much additional power is needed if an input pin is driven lower than VCC, your supply rail. IL is the input leakage current. This is how much current the device uses due to the current flowing into the input pins when the device is powered off. So it's useful for standby power calculations. It's important to realize that all of these current measurements are based on a certain amount of external capacitance at the input and output pins. These values are seen in CI, capacitance in, and CO, capacitance out. And they give you the maximum capacitance values that the device can drive into. The dynamic characteristics tell you how the device will respond to changes to the input and output pins. Remember that CMOS devices are very low power when the inputs are fixed. but they consume the maximum power when they are transitioning from one state to another. The propagation delay, TPD, tells you how fast a signal can pass through the device from the input to the output side. Since that depends on the output drive required, there are different values depending on the output capacitance. The power dissipation capacitance value is needed to calculate this value. Just like your car uses more gasoline the faster you go, so does a gate as it runs faster and faster. Now the actual equation that uses this value is listed at the bottom of the table, so you can calculate the real power for any particular speed of operation of this device. Did you know that some parts actually have a lower speed limit? In this case, you will find that there's a note in the datasheet, typically under the recommended operating conditions, that lists minimum delta T, delta V input transition rise and fall rates. What this means is don't try to operate slower than this value. My circuit doesn't work in the lab. One of the best tools for debugging in the lab is the oscilloscope. This tool gives you a graphical representation of the signals on the logic device as they change over time. In the same way, the waveform section of the datasheet shows you the way that your signal should look, as well as the actual values for voltage and time that you should see. By the way, the most common issue with logic devices not working properly is a violation of the setup time. If those signals are not nice and stable when the device reads them, you may get some very unexpected results. So check that first if your circuit isn't working. Remember before when we talked about true Schmitt triggers and action? Here's the data that confirms that this particular device has true Schmitt trigger inputs, a listing of the transfer characteristics. These tell you how far the voltage must swing in one direction before it can return and then be detected as a new signal transition. If you got a noisy input signal, you definitely want this feature. And here are the detailed package outlines that we mentioned before. You can use these dimensions to see how much board space you need for a particular device, or to create your own custom solder footprint. The best news is that these SOT packages are industry standards. A SOT 108-1 will always have the same dimensions regardless of who makes it. And finally, wrapping up the datasheet is a listing of all of the revisions of the device, as well as a list of all the abbreviations used. Save yourself some trouble. Always use the latest revision. So there you have it. A quick visit of a logic datasheet. Most of your answers are there. You just need to know where to look for them. But remember, if you still can't find your answer, don't hesitate to call your local FAE. Now, go out and design something.